So now that we've simplified down the entropy balance, we need to develop functional forms for all of the molar entropies of the streams. To do that, we're just going to turn to the fundamental entropy equation. So to get SI, can use fundamental entropy equation. Yeah. All right. And so with the fundamental entropy equation, we could just start here. Plus P over T dV. And if you use the ideal gas law, which you saw in chapter 4 in class problem 4, you're able to convert the fundamental entropy equation into this form, where now the main variables we care about are temperature and pressure, which is the exact properties we were given in the problem. So if you integrate this equation out, what you get is your delta. I'll write out the integral ds, and we'll focus on entropy 1 first. You integrate that, you're going to get delta S1, and the delta in this case is referring to S1 minus the reference entropy. But as we've seen before, at the reference state, your entropy is going to be 0 at ref conditions. Okay. So really all you're left with is just the S1 that we're calculating. So from our integral, we get this T1 over T ref minus our ln of P1 over P ref, and technically there's a minus 0 here, right? This, okay? All right, and so you could use the same approach for all of the molar entropies we're dealing with. So I'll write them here. I'll move this down just a bit. Put it here. S2. S3. Same sort of functional form. Now, when we were talking about enthalpies earlier, I mentioned that in the enthalpy formulas we derived, there's no pressure term, right? So the enthalpies for an ideal gas were unaffected by pressure. But here, when we look at the entropies, we see there's an explicit pressure term in there. So one thing I want to emphasize is that the ideal gas entropies are affected by pressure. And that's going to play an important role coming up. Okay? All right. So we have functional forms for all our entropies. So let's go back to our entropy balance and plug that in. So we have 0 is equal to the CP. And what I'm going to do is I'm going to sort of combine terms here. So first, I'm going to focus just on the temperature terms. So here what we have is, and what I'm going to do here is I'm going to employ the log rules, where this natural log of T1 over T ref, that's the same thing as the difference between ln of T1 minus ln of T ref. Right, that's just one of the log rules. So here I'll write ln of T1 minus ln of Tref. That's one term. Then we have the entropy 2 temperature term. 1/2 ln of T2 minus ln of Tref. Then we're going to have the entropy 3 temperature term. Ln of T3 minus ln of Tref. Right, and that's all the temperature terms. So now I'm going to go to the next line. All right, and now I'm going to focus on the pressure terms, and I'm going to write it like this. So first I'm going to write plus R. You'll notice that there's a negative R there. What I'm going to do is I'm going to incorporate that negative inside the parentheses. So we'll first start with the entropy 1 pressure terms. So we have negative ln of P1 plus ln of Pref, right? And then we're going to have plus 1/2 negative ln of P2 plus ln of Pref plus 1/2 negative ln of P3 plus ln Pref. Okay. All right. And so, here the terms are arranged by temperatures and pressures. And the reason I did that is because same thing that you saw with the enthalpies. If you notice with all the T refs and the P refs, they're all going to cancel out. Right? So you don't even need to worry about those whatsoever. All right, and if you simplify down this equation, what you get is 0 is equal to CP. And then now I'm going to employ the log rules. And you'll get this. So ln T1/2 squared over T2, T3, or T1 squared. Okay, you know that. And then minus R ln of P1 squared over P2, P3. Okay, and I guess I'll put square parentheses there. Okay, and the square here comes from playing around with the log rules and also taking advantage of the fact that you have this 1/2 term here. Okay, all right. So then, one other thing we'll point out: P2 and P3 are going to be the same. So we'll replace that with P2. Okay. All right, and then keep simplifying this equation down. You get CP is ln, or actually, oops. What we'll do here is we'll further take advantage of the log rules. And anytime you have a coefficient multiplied in front of a log, you could actually move it to the exponent's place. So here, minus ln P1 over P2, since both of these are now squared, you can move that to the exponent's place. We'll also move the r to the exponent's place. So that becomes a 2r. Okay. All right, and so now at this point with this equation, our unknowns are still T2 and T3. But if we combine it with the equation we got from the energy balance, then we'll have two equations and two unknowns, and we'll be able to solve. Okay? All right, so we'll do just that. Combine 1 and 3. Okay. So if you combine the two, you get this equation for T1. Oops. This is going to be 2R over CP. Let's raise to the 1/2. Okay. And we know everything on the right-hand side here. So all you have to do is plug in. When you plug in, you get 437 Kelvin. Then once you have your T3, you go back to the energy balance equation. And we could solve for T2 now. You get 159K. Right? And so the inlet stream, that was at 298K. But after it passes through the vortex tube, you get a hot stream that's at 437K and a cold stream that's at 159K. And the delta T between the two is equal to 278 Kelvin. All right? And so through this problem, by proceeding through the energy and entropy balances, we showed that, you could have a device that could separate a stream out, but one that, obeys all the thermodynamic laws, right? Energy is conserved, and also the entropy that's, well, we're running a reversible process, so there's no entropy generated, right? We don't have a negative entropy generated term. And really, the reason that we were able to do that goes back to that point I made about how the entropies that we calculated do have a pressure dependence here, okay? And so in order for the separation of the middle stream into a hot and cold stream, in order for it to proceed, it's actually not really driven by temperature changes, but rather the separation is driven by differences in pressure between the inlet and outlet. Okay. All right. So air at higher pressure has an entropy lower than air at low P. Okay? And so in this process, you go from high pressure to low pressure. Okay? And based on the entropy differences here, your pressure term is negative here, right? And so the higher the pressure is in this term, the more it subtracts off the entropy. And so P2 and P3 have lower pressures than P1, right? And so if you lower your pressure, that means this term is going to get smaller and your entropy is going to get higher. Okay. All right. So the pressure drop leads to an increase in entropy for the air in the cold and hot outlet streams. Okay. All right. And so, by going through the material, energy, and entropy balances very carefully, we could show that for a vortex tube, it's thermodynamically feasible for it to separate out one stream into a hot and cold stream.